So let's make an object, kind of old looking object, following shape. The mass of the object is going to be concentrated in the circles, and we're going to join those objects with very light bars. So the mass of the object, as I said, is concentrated in the circles. The bars don't add up to the mass of the object, and we're going to make this structure rigid by adding bars connecting the different points. Now let's say that we spin this object with respect to a certain axis. Let's say that we set up an axis of rotation here that is perpendicular to the screen. So we're gonna, as we're gonna explain it, we're gonna put a torque on this thing and make it start spinning. But at this point, the object is already moving, right? So each one of these masses is going to have a certain velocity. So let's say that this is mass 1, so we'll have a velocity v1. Mass 2 will have a velocity v2. Mass 3, as the object is spinning in, say, this direction. Mass 3 has a velocity v3. 4 will have a velocity. Now the question is, how much kinetic energy do these masses have? So the total amount of kinetic energy of this object is going to be equal to the sum of the kinetic energy of each of its parts. So it's going to be 1/2 of mass 1 times its velocity square plus 1/2 of mass 2 times its velocity square plus 1/2 of mass 3 its velocity square, and so forth and so on, as many masses as you have in this object. So that's the total kinetic energy. Now, because the object is rigid, all the masses are not free to move in any way they choose. They have to remain together, right? Because if the object is rigid, the shape of the object remains constant as it spins around the axis, and that constancy in the shape of the object means that the masses that make up the object are not free to move in any way they want. So what is the relationship that they have? Well, in circular motion, as you remember, we have that when an object, say this object attached to a string or rod, spinning around this point, then the velocity of the object is related to something that we call the angular velocity, omega. Omega, we find it as the rate of change of the angle. Right? That angle can define some reference axis and measure or localize the position and localize the object by specifying the angle that the vector position makes with some fixed axis, which we call this one the x-axis. So as the object spins around, the angle theta changes, and the rate of change of that angle with respect to time is what we call the angular velocity. So there is a connection between v, the velocity, the linear or tangential velocity of the object in circular motion, and omega. We talked about this before. We know that there's a connection because the angle in radians is defined as the length of the arc. This is all in a circumference, part of the circumference. So let's say that the circle has a radial arc. So the angle theta in radians is defined as the length of that arc divided by r. So if you take the derivative of theta with respect to time, d theta dt, this equation, for circular motion the radius is not changing, so you get ds dt. The distance that the object covers along the circumference of the circle, what distance over an amount of time, ds dt. So this ds dt term is clearly the tangential velocity of the object. I'm just going to call it v. So d theta dt is equal to v divided by r. Since we call d theta dt omega, then the connection between v and omega is that v is equal to omega times r. So any object that moves in a circle has a tangential velocity that is equal to the angular velocity times the distance at which the object is spinning from the center of rotation. So going back to our expression for the kinetic energy of the object, remember that we had this object that's made of different pieces and spinning about an axis. So that this is the point about which it was spinning. So each one of these objects had a velocity, but those velocities are all connected. The kinetic energy of the object is 1/2 of m1v1 square plus 1/2 m2v2 square plus 1/2 of m3v3 square, and so on. Now, v1 has to be equal to the angular velocity of this rigid object as it spins around the axis, multiplied by the distance at which the mass 1 here is from the axis of rotation. So that distance is going to be this distance, that is r1. r2 is the distance at which the object number 2 is spinning about the axis of rotation. So if we use all those r's to express the velocities in terms of omega r, then we get that omega r1 square, that's v1 square, this term over here. If you add to that 1/2 of m2 times the velocity of object 2 square, the velocity of that object must be omega, and the same omega as before, r3 whole b square, plus you will add as many terms as particles that make up your object. So your kinetic energy, you can write it in terms of, why don't we factor out what's common to every term, which is the term omega squared. So the kinetic energy is going to be equal to 1/2 of m1 r1 square plus 1/2 of m2 r2 square plus everything multiplied by omega squared, since omega squared is in each one of the terms that make up the summation. 1/2 of m1 r1 square plus m2 r2 square, and all of those terms multiplied by omega squared. So we can write the kinetic energy for any object as 1/2 of the sum of all of these products, where I goes from 1 to n, as where n is the number of pieces that make up the object, times omega square. So as usual in physics, we give name to the quantities that show up frequently, and this is one of the quantities that shows up frequently when dealing with rotational motion. It's the sum of the product of the masses of the objects multiplied by the distances from the center of rotation. So this thing is called, it's given the letter capital I, and the name of the quantity is moment of inertia. So the kinetic energy of a rotating object can always be written in terms of the moment of inertia and the angular velocity of the object. So notice that this is the equivalent for rotational motion to the kinetic energy that we have for linear motion, which is 1/2 of the mass times the velocity squared. The quantity that plays the role in rotational motion, the role of the mass in linear motion, is the moment of inertia, and the quantity that plays the role of velocity is the angular velocity. So far we have learned how to calculate the moment of inertia for point masses, either one point mass or an object made of several point masses, where all the mass of the object is concentrated at specific points. An important question is, what is, or how do you calculate the moment of inertia for a continuous distribution of mass, when the object is it has its mass uniformly distributed all over the volume? Or we can still use the definition of, we can start by using the calculation for the moment of inertia that we saw before, where if the object is made up of discrete masses, then each mass multiplied by its distance to the center of rotation square, and when you add all of these contributions, you get the moment of inertia of the whole object. For a continuous distribution of mass, the one shown here, suppose that the center of rotation is where it's indicated. What we have to do is basically divide the object into small pieces. So we can slice it vertically, horizontally, so that we get small pieces. And we can label each one of the pieces, 1, 2, 3, and so on. So the piece I, which has a mass m sub I, is at a distance r sub I from the axis of rotation, and therefore this piece will contribute to the overall moment of inertia of the object with an amount m sub I r sub I squared. Of course, this is not the only piece that makes up the object, so we have to sum over all of the pieces to obtain the total moment of inertia of this object. Now these pieces, to make this quantity exact, each one of these pieces will have to be very small, because remember that the definition of moment of inertia applies to point masses. So in the limit, when the slicing is very, very, very fine, then each piece will have a mass, an infinitesimal mass, dm, and the summation has to be replaced by an integral. Each of the masses is at a distance r squared, so we need to integrate over the whole body of the object the amount dm times r squared. We're not going to go into the details of how to calculate these integrals. Whenever you need the moment of inertia of the continuous distribution of mass, like a disk, cylinder, square, whatever it is, you can look it up in the table in the book. But what's important, of course, is to understand how to calculate the moment of inertia for discrete masses, and the principle behind the calculation for the continuous distribution of mass.
We're talking about moment of inertia last class, right? We had a demo, somebody volunteered to test these two rods, remember? The rods have the same weight. If you hold them, they feel about the same. They have exactly the same weight if you measure them. But the rotational motion of these two rods is very different. I can shake this one very fast. I can hardly shake this, maybe half the speed of this one, right? So there's a very, very big difference in how you can rotate the rotational inertia, as we call it. So this one, we explained that the reason why this one's a lot more sluggish, it's because the weights, which is the same as this one, it has two weights, they are located here and here. So they're far away from the axis of rotation that you have. So your hand is putting a torque, that's what we're going to talk about today, that is making this thing spin, and the sluggishness of it depends on not only the mass, but where that mass is located in the object. Okay? In this in this rod, the two masses are very close to the center. So if I try to spin it by holding it in the middle, then it fits easy, even though you're basically moving the same amount of mass.
Please calculate the moment of inertia of the blue rod with respect to the center and the moment of inertia of the red rod with respect to the center. Leave the calculation in terms of M and L, and then go to Allspace and select the correct answer.
Another thing that we said that was very important when talking about moment of inertia is that it's not just it's a number, right? But you have to always specify about which axis you measured it, right? If you ask me what's the moment of inertia of this board, and I said, 2 kilograms meters square, that doesn't really tell you much, because you don't know about which point that moment of inertia is, right? So I have to tell you it's 2 kilograms meters square with respect to this point, or with respect to this point, or any point that you're trying to use as your axis of rotation. You would like to know what's the moment of inertia with respect to that point. Okay? So it's not a specific or an intrinsic property of an object. Moment of inertia is not. Mass is, moment of inertia is not. It depends on where you're going to put your axis of rotation. Okay? So you want to always specify measure with respect to what? Measure with respect to the center of mass, or is it measured with respect to point A, or is it measured with respect to point B? This might be the center of mass, this might be point A, this might be point B. The moment of inertia with respect to A, with respect to B, with respect to the center of mass, those are going to be different numbers. Okay? So which one to use is going to depend on the kind of problem that you're trying to solve. It's going to depend on about which point is the object supposed to be rotating, or about which point the object might rotate if you had a net torque acting on it. Okay, so it's going to depend on the problem.
Now do the calculation for the moment of inertia of the blue rod and the red rod, but now with respect to their bottom end. Go to Outspace and choose the correct answer.
Let's say that you have two objects and they have the same radius. It might be made of different material, but they have the same mass and the same radius. So this is R and the mass is M, and this and it has the same radius. Let's call this one A and this one B. How does the moment of inertia of A compare to the moment of inertia of B? Is it bigger? Is it smaller? Or is it the same? We're going to compare the moment of inertia of A with B as measured with respect to, okay, so let's say that this is the axis of rotation. So now it is clearly specified, and then you can answer the question. So which one's bigger? The answer is the moment of inertia of A is bigger than the moment of inertia of B. The reason being that the mass is the same, right? But the question is, where is that mass located? Right? If you look at this object, you see that most of the mass is located very close to a distance r from the center, right? So you would say that the moment of inertia of this thing, just a rough calculation, if it's not too thick, you would say that you're going to expect a number that is very close to this, depending on the thickness of this, right? But the moment of inertia of B, when you look at the distribution of mass, you can claim that most of the mass is located at the distance r. It's pretty evident that that's not the case. You have a lot of mass here, close to the axis of rotation. So that mass is not going to contribute as much as if it was located at a distance r from the center. Okay? So that definitely decreases the moment of inertia with respect to this object. Critical thing here is that we're talking about the same mass, same radius. Okay? So it's going to be less than mr squared. And in fact, if you do this calculation, you would have to do an integration. I'm not going to ask you to do that. You can look at the result or the table with different moments of inertia for different objects. You can look it up in your book. This is going to be 1/2 of mr squared. Okay? So definitely less than mr squared.